Hello, welcome to my video. In this video, we're going to be discussing the question, how many ways are there to tile an n by m chessboard with 1 by 1 tiles and 2 by 2 tiles? So let's create some drawings and visualize really what this question is asking and what kind of objects we're looking at. So by an n by m chessboard, we mean some rectangular chessboard, some rectangular grid of squares that look something like this. This is an example of a 4 by 3. So if n is 4 and m is 3, this is what our chessboard looks like. And then we're looking at the ways to cover this chessboard in tiles, where the tiles are either 1 by 1, like that, or 2 by 2, which would cover 4 squares total, like that. Okay, so now let's visualize some of the actual tilings that we're looking at, because we're looking at ways to tile these kinds of rectangles using these 1 by 1 and 2 by 2 tiles. So these are some examples. So this is one n by m chessboard, and if we let the white shaded areas be our 2 by 2 tiles and the other black squares be our 1 by 1 tiles, we see that this is a possible tiling. This is a possible arrangement of our tiles covering this chessboard. And then here we have a different n by m chessboard with a different tiling, because this has 2 by 2 squares here and here, and the rest of them being 1 by 1 squares. Okay, so in order to actually count the number of tilings we're going to have to limit one of our dimensions and use what's called the transfer matrix method. So for now, we're just going to investigate how many ways there are to tile in n by 3. It's n by 3 because it has a length of n, where we don't really care, we're not restricting this dimension, but we are restricting this dimension to be 3. And then we're going to investigate the different types of intersection points we can have. Intersection points being like that right there. Like these vertical lines, all these different vertical lines, what could they look like? So we're going to split them up into different types. So type A is going to look like 3 vertical lines. It's going to look like 3 vertical lines where squares start before them and squares start after them, but they're not being covered by anything. And then if we look at type B, we'll call what's going on here to be type B. This vertical intersection point right here. It's being covered by a big square, by a 2 by 2 tile. So it's being covered, so these are really being covered. So we have like a blank here and a blank here, and then after that we have an actual intersection where there's a square to the left of it and a square to the right of it. And then similarly, we can see somewhere like here, we have what we'll call type C, where we have an actual line above it and then 2 blank spaces that are being covered by that big square. Okay, and then once we have these types laid out, type A, type B, type C, we're going to create a matrix where we're going to let the columns represent starting at one of your types, and we're going to let the rows represent ending at a given type. So to fill this 1 by 1 spot, this 1, 1 position, this entry, we're going to think about the ways where you can start at type A and then go 1 intersection point over and end at another type A. How many ways are there to do that? There's only one way to do that. It comes if we place a little square here, a little square here, a little square here. So there's only one way to get from A to A. And then similarly, we're going to think about how many ways we can start at A and end at type B. So in order to go from type A to type B, we would have to place a big square here to cover this little intersection point here and have a gap, and then place a little square here. And there's only one way to do that. Similarly, there's only one way to go from type A to type C. Okay, now we'll look at how many ways to go from type B to type A, from type B to type A, which would go right here. And so, since this is covered here, we know that this is really a big square that's going over this and filling like that next intersection point. So the next intersection point is going to have lines up here. So it can't have any gaps in this position or this position, which means that we're forced to go to type A after type B, because the only thing that we really have freedom to do is fill this square with a little square, because we can't place a big square there, there's not space. and these are already filled with half of a big square. So you can only go to type A, and you can't go to type B or type C. And then similarly, we see that C is just a mirror image of B. It's going to have the same exact entries. Okay, so we have our actual matrix here. We're going to call it a transfer matrix. And this is telling us that if I want to go from type A to type A, there's one way to do that in one step. Type A to type B, there's one way to do that in one step also, and so on. And the idea is, if we raise this to the nth power, that's going to tell us, all of these entries are going to tell us how many ways to go from A to A in n steps, or from A to B in n steps, as opposed to the immediate adjacent intersection point. It's going to be the nth adjacent point, or the nth intersection point after that. And really, since we have these rectangular chessboards that we're trying to tile, we only care about going from type A to type A. Because remember, type A was all lines. So we're starting at all lines, and we want to end at a rectangle, so we want to end at all lines. So what we're going to do is we're going to raise this to the nth power, and then multiply by the appropriate matrices to extract the eighth position. But not eighth, the AA position. Okay, so that general line of thinking of how to make the transfer matrix is going to keep applying, and we can think about all these different types of rectangular chessboards, where we have an n by 2, this is the transfer matrix for that, an n by 3, this would be the transfer matrix for that, this is the one we just looked at. N by 4 would have a transfer matrix that looks like this, n by 5 would have a transfer matrix that looks like this. And for all of these, to find out how many ways are there to tile, say, a 6 by 5 chessboard, what we would do is we would take this transfer matrix, raise it to the 6th power, and then look at the 1-1 position of the 6th power of this. Similarly, if we wanted to look at how many ways there are to tile a 38 by 4 chessboard, what we would do is we would take our n by 4 transfer matrix, raise it to the 38th power, and look at the 1-1 position. So these transfer matrices are going to be our objects for counting the ways to tile a n by 2, n by 3, n by 4, n by 5, and we can keep making them. And we can keep making ones for n by 6, and n by 7, and n by 8. But remember that our original question was to try to investigate how many ways there are to tile an m by n. And right now, we've generalized this first dimension in all these cases, but we're restricting the second dimension, which is a problem. We want to try and figure out how to fully generalize it in both dimensions. So what we're going to do is we're going to look at the similarities between all these transfer matrices and try to think about what the transfer matrix would look like in the nth case, no matter what this second dimension is. So we're going to take a moment and we're just going to stare at all of these transfer matrices we have and think about what similarities they have and why these similarities might be popping up. So let's take a moment and think about the size of each matrix. In the n by 2 case, it's a 2 by 2 matrix. In the n by 3 case, we have a 3 by 3 matrix. In the n by 4, we have a 5 by 5 matrix. And in the n by 5 case, we have an 8 by 8 matrix. And if these numbers look familiar, 2, 3, 5, and 8, they should look familiar. These are actually the Fibonacci numbers, which are denoted Fn. So let's try to think about why this is actually happening. We're going to come back to that in a minute. But it's not a coincidence. These are, in fact, the Fibonacci numbers, and they're coming up for a really good reason. So the size of our matrices, of our transfer matrix, is going to be determined by, or maybe let me call it Fm, because it's this second number is determining which Fibonacci number we're looking at. Okay, what else can we notice just from staring at these matrices? We notice that they can only have 1s or 0s in them. We never see any 2s pop up, we never see any 3s or 4s. It's always just going to be 1s or 0s. And then another important thing to notice is that the main diagonal of these matrices, other than the 1-1 position, is always full of 0s. Look at that. So other than the 1, 1 position, the main diagonal is always going to be filled with zeros. So we were able to come up with a bunch of conjectures just by staring at all of the different transfer matrices we had. So let's investigate this first conjecture we had about the matrix size. We said that the size of the matrix that counts how many ways to tile in M by N is going to be the nth Fibonacci number, where N just being the second dimension. So let's think about why that might be the case. And in order to do that, we're going to remind ourselves that the size of our matrix had to do with how many different types of intersections we had when we were making the matrix. So let's visualize that in one of our cases. Okay, so here we have drawn out all of the possible types of intersections we can have in the n by 4. We can either have all vertical squares ending, we can have one big square overlapping and then a square ending and a square ending, or we can have a little square ending, the overlap of a 2 by 2, a square ending, and so on. And if we take a moment and we stare at this and we think about this and we try to justify why the number of different types is the nth Fibonacci number, and we can see that this is just an equivalent question to how many ways there are to tile an n by 1 board with squares and dominoes. We know that the number of ways to tile an n by 1 board with squares and dominoes is counted by the nth Fibonacci number. And if we stare at these different types, we're going to see that if we just replace our vertical bars by squares and our vertical gaps that come in pairs by dominoes, it's just the same exact question. So like for this one, to convert this to a square domino tiling, this would look like square, 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 square. And this one would look like domino, square, square. And this one would look like square, domino, square, 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 domino, domino, domino. And since we know that the square domino timings of an n by 1 is counted by the nth Fibonacci number, and we see that these are equivalent questions, we can assert that there's definitely going to be fn different types, and so we can conclude that our transfer matrix size is going to be determined by the nth Fibonacci number as well. Okay, so now let's investigate this other conjecture we had that only zeros or ones can appear as the entries in our matrix. So this is going to come down to how many ways there are to go between types. And if we think about it, if I want to think about all the ways that type A can go to type B, or type B can go to type C, or type B can go to type D, or type E can go to type C, and so on. Well, there's either going to be 0 ways, there's going to be no ways to do it, or if there's a way to do it, it's really just going to come down to where we place our big squares. So if I want to go from type A to type C, I can see exactly the way I need to tile after type A. I would need to place a big square here, so that the next intersection point looks like line, gap, line. And there's no other way that I can do that because I really only have the one tile I can play with, the big one. The big one determines where the gaps actually go. So there's only ever going to be either no ways to get somewhere or just one way, and that one way is just that one place where I have to put the big tiles. Okay, now let's investigate this last conjecture we had, that the main diagonal is going to have to be filled with zeros, except for the 1, 1 position. So let's investigate this except for the 1, 1 position. The 1, 1 position is always going to represent from type A, which will always look like all lines, to type A. And there's always going to be one way to go from all lines to all lines. It's going to be by putting all little squares right next to the intersection point, so the next intersection point is also all lines. So there's always going to be one way to do that if we just put all little squares right next to the intersection. However, if we take a look at any of the other types, they're going to have some big squares in it. So since this has a big square in it, we can kind of like look at the immediate area around it. We know that a big square is going over this intersection point. That means at the next intersection point, there has to be lines here, because the big square has already been placed. So there's no way to go from a place with gaps on it, up here in the top two positions, to another type B, which would also have gaps in the top two positions. Because there has to be lines in the top two positions, because there's a big square in these top two positions. So any of these types that have gaps in it, those gaps represent big squares. And so you can't go from a gap here to another gap in that same place, because there's this big square in the way that's already been placed that determines that we have to have a line up here. So type B can never go to type B. Type C can never go to type C, and so on, because they have big squares already placed. And so our main diagonal is going to have to be filled with zeros, except for in that 1, 1 position. And really, after a semester of research, those are our only findings about the number of ways to tile an M by N chessboard. We weren't able to come to an actual generalization, but we were able to make a bunch of these different matrices, find a bunch of numbers, and think about how to generalize the transfer matrix for the M by N case. And so we have these conclusions about the structure of these matrices, but for now, that's all we have.